Thanks. It's a real pleasure to speak here today and to be back at CITA. I'd like to tell you about a new balloon mission we're developing at NASA Goddard with a number of collaborators. At the largest level, the goal of Exclaim is to learn more about the question, how did we get here? So in particular, how did the universe evolve from the nearly homogeneous gas of hydrogen and helium at the time of the CMB to the rich structure that we inhabit today? There are two approaches to learning about this history. One I would call bottom-up, and that is to resolve individual galaxies and their properties and then infer those properties in aggregate and across redshift. And the other I would call top-down, and that is to start by measuring that aggregate, and ultimately the two need to agree. So one place where this has been especially fruitful is in the 4IR background. In 1998, FIRAS released a measurement of the 4IR monopole. So this is an integral of all dust emission of galaxies at all redshifts. So this represents the total starlight that's been reprocessed by thermal dust emission. And that turns out to be about half of the total starlight. On the side of resolving the sources of that emission, FIRAS in some sense threw down the gauntlet for 20 years of very fruitful observational studies of individual sources that have sought to resolve this background. So here I show BLAST, it's a bit hard to read, ALMA and Herschel as examples of these sorts of efforts. So the 4IR background, being a continuum, doesn't contain a lot of redshift information. And moving forward, we'd like to be able to better resolve the evolution of galaxies over the history of the universe. So in particular, it's known now that since the time stars have formed, there's been a rapid increase in the star formation rate until about redshift 2, followed by a fairly precipitous decline of about a factor of 20 to the present. So we'd like to learn more about why this evolution took place. For example, is this due to the abundance of molecular gas over time, or more the efficiency of star formation from that gas? And to answer those sorts of questions, we'd like to measure the abundance and phases or excitation of those gases. So to do this, we'll look at atomic lines, and that also provides redshift information. I'm really bringing the coals to Newcastle here to talk about intensity mapping. So I'll try to put maybe a couple different spins on it. This is a place where many of the essential measurements of intensity mapping have been made. The basic principle, though, is that in an ordinary galaxy survey, one will map the redshift, RA and DEC of a large number of objects and situate those in a three-dimensional volume. So the point of intensity mapping is to ask, well, maybe we can learn nearly the same amount by taking our glasses off and seeing the structure of the overdensities. And in particular, if there's a line emission from objects at this redshift, that will show up in emission at a discrete frequency. So that allows you to make a sort of an MRI of the structure of density and emission in the universe. This is a study done by Tony Lee for COMAP with the CO10 transition, and this is in the frequency direction, so slicing backward in time, and in the angular direction of that survey. So this approach had its origins, I think, or at least was stimulated by work of Sunayva and Zoldovich in the early 70s. The first paper which I think identifies the key areas of intensity mapping, though, was Hogan and Rees, 1979. And they made a couple points that I think are still essential to the approach as it's followed today. One is that this allows you to measure all objects, not just the brightest objects. So today we'd say it's a complete blind census. And the second point they make is to use narrow bands. So here you can imagine these are structures from their paper in 1979, and they would like to resolve these individual structures. And if the spectral band is too wide, it will wash out the density contrast. Third, they did correctly identify that there's also a lot of continuum emission that is effectively a foreground to this measurement, because most of the radiation in the universe isn't reprocessed by line emission. So here they point out that foreground or continuum emission should be spectrally smooth, whereas this intensity should have spectral signature. The first paper that I'm aware of to seek intensity mapping as an experimental method was Bebbington, 1986. If anybody knows of an earlier effort, I'd be very interested to learn about it. This was, I think, the first study of the reionization era with 21 centimeter, and they did a novel frequency differencing technique to subtract the continuum. So here you see the RMS in their clean map. They show was less than 2.5 Kelvin. So a slightly more modern set of motivations is shown here, and the first is the aperture. So for observations that seek to detect individual sources, flux sensitivity drives large apertures, as does avoiding the confusion limit. In contrast, intensity mapping is more of a study of surface brightness rather than flux. So the aperture size matters really sort of at second order. The second major area that we still is still an essential part of the effort today is that it's sensitive to all objects. So it's a complete blind census, plus all other forms of radiation as contamination. An additional area that's relevant today is that these surveys can cover very large volumes, and in doing so avoid problems with cosmic variance in smaller area sky surveys, where you could be surveying a factor of 3 over dense compared to the cosmic average. I'll show on the next slide, but there are a wide variety of lines that trace different environments and ionization states to learn about different aspects of galaxies over time. And it's also important to point out that this is a cosmological measurement. So the clustering is biased, and that bias tells you about the mass of the host halos that the galaxies and stars inhabit. And finally, there's a completely different set of systematics, namely there's no selection function. On this slide, I talk about the tracers and some existing detections of those tracers. To see where these are in a galaxy, I have this cartoon here showing the IgM after reionization, where the gas is fully ionized. Denser gas can self-shield and become neutral, and that's traced by 21 centimeter radiation. That neutral gas can continue to cool and become molecular. That's well traced by CO, not the H2 itself, and also neutral carbon. That cold gas can collapse into luminous objects, and those ionize and excite other species nearby, and that's traced well by C2, H2, N2. So 21 centimeter has a number of detections now at low redshift in cross-correlation. CO has an initial detection in autopower with the COP survey that I cite here. C2 has a preliminary indication. Work by Anthony Pullen in the last 2 years has shown that there's an excess that's consistent with C2 emission. Lyman alpha traces star formation, but also some of the complexities of radiative transport around galaxies. And you should also really think of the cosmic infrared background as an intensity map, even though it's only two-dimensional. So in all of these, there are still continuum foregrounds that may be of order tens to hundreds, up to 10 to the 4 times brighter than the signals of interest. And this has interesting implications for dynamic range and calibration of instruments. So I've sometimes struggled in explaining whether there's any unified way to understand all the intensity mapping efforts that are ongoing now. So I made this diagram, which I think explains some of the underlying motivation. So early on, there's this point of being able to observe reionization and the early universe, which are difficult in any other way. But there is some agitation that, well, it'll be 10 years before we ever see reionization, so it's something we can do sooner. And then the motivation was that spectroscopic samples are expensive, and 21 centimeter emission at lower redshift may be detectable and allow studies of dark energy or non-Gaussianity. And then again, there was some agitation that, well, we might be 10 years from detecting the BAO, so is there something we can do sooner? And that's this other sort of species of studies of galaxy evolution. This is primarily what I'll talk about. And here there have been detections of CO, C2, Lyman alpha, and H1 at lower redshifts. Each one of these sort of main efforts has manifestation in instruments. So now large interferometers that have bound 21 centimeter emission at high redshift, and studies of the search for the BAO, with CHIME, I think, being the best example of these studies for dark energy. This is a best effort at compiling the list of all ongoing and near-term intensity mapping experiments. I'm happy to put this up at the end or send people a copy. I realize it's a bit hard to read just because of the total number of them. There's you see a wide diversity of lines, so 21 centimeter C2, CO, and Lyman alpha. Wide variety of science targets, from star formation, large-scale structure, reionization across different redshifts, frequencies. And I think from an experimental point of view, it's also interesting that there's a very wide range of new technical approaches for going after these signals. If anybody is aware of anything missing from this table, please let me know too, as I'd like to include it. There have been similar efforts to show the space of experiments, nicely summarized in Eli Kovitz's summary of the state of intensity mapping in 2017, and then in a decadal white paper this year. In 2017, this shows the resolution and survey area as well as the redshifts. You can see that these experiments have a great ambition to cover a wide range of redshift and area with a number of lines. And then in the recent decadal paper, there's a connection between these experiments and particular lines. So sort of like the grass diagram that I just had. Okay, so I'd like to move to talking about Exclaim specifically. This is a balloon-borne mission to map redshifted CO and C2. It stands for Experiment for Cryogenic Large Aperture Intensity Mapping. This is a preliminary logo. Any other recommendations are welcome. We just received full funding about 2 weeks ago, so this is really getting started now. The mission's led out of NASA Goddard, and we have collaborators at a number of institutions. Arizona will be providing the readout. There's an active science effort at CCA, CITA, and NYU. If you're interested in learning more, I'd be very eager to talk to discuss interests. Maryland is involved in the instrument and science, and Michigan is also participating in the instrument design. So moving specifically into Exclaim's goals, we'd like to learn more about the factors that led to this dramatic decline in the star formation rate since redshift 2. So why is it that dark matter has collapsed 100-fold while the star formation rate has declined 20-fold, and only 5% of baryons end up in stars? So to learn about that, we would like to measure the abundance, excitation, and evolution of the molecular gas which forms stars, and the gas which is influenced by stars. Additionally, we'll have a galactic field, and the primary goal there will be to measure neutral carbon. So neutral carbon can live in regions that have molecular H2 gas, but where CO is photodissociated. So this is so-called dark molecular gas. And by measuring neutral carbon in our own galaxy, we can learn something about how well CO traces a molecular gas more generally. And finally, this is a pathfinder. So this is meant to have an initial detection in cross-correlation and measure parameters and test approaches that could be used to, for example, probe higher redshifts or measure these quantities with higher precision. I think it's interesting to look at some of the language in recent decadal surveys, which I think have been useful in supporting intensity mapping. So these are from the US decadal survey. So from the previous, they cited how do baryons cycle in and out of galaxies, and what do they do well there, and what are the connections between dark and luminous matter. So really directly the bias of this emitting gas. And then in an interim report, there's a citation to completely map the contents, selected volumes of space that represent slices of all cosmic time. So basically, exactly intensity mapping. So I think it's important for the community to hone and retain language like this in upcoming decadal reports, as this is quite valuable for having efforts like this proceed. Also mentioned that programmatically intensity mapping is interesting for NASA because it has much lower requirements on aperture, and aperture drives cost. Additionally, the focus is really on photon backgrounds, so novel instruments with new approaches to detector technology. And then finally, many of the frequencies of interest just aren't accessible from the ground, so that makes it compelling to do from NASA. In the bottom right, I show simulations from populated into the mice simulation for a subregion of the Exclaim survey, just to show some of the principle of it. So the idea will be to cover a large area. If you look at a small area and sample a discrete set of galaxies, it could be that that area has an overdensity or an underdensity, so it may not represent a cosmic mean. But by covering a larger area in this broader distribution of structure, we could hope to measure the mean emission. So moving specifically into the lines that we would like to constrain, the spectrometer will observe between 420 and 540 gigahertz with a resolving power of 512. And the primary science will be in cross-correlation with BOSS. So if there's any auto power, that's incidental, but not the primary effort. C2 will be in cross-correlation with the quasars at redshifts similar to work done by Anthony Poland, so from redshift 2.5 to 3.5. What we'd like to do with this is make a definitive test of this preliminary detection that I show here in purple. This is a log scale. It's a bit hard to tell, but the Exclaim band sensitivity would be down here. So our hope is that we can make a definitive detection either of C2 emission in this bright range of models that are collisional or from this lower model. For CO, we'll have two ladder lines for each of the main BOSS catalogs. So for the Sloan main sample between redshift 0 and 0.2, we'll have J54 and J43. For low Z, 0.2 to 0.4, I'll have the next ladder lines up. For CMAS, between 0.4 and 0.7, we'll have 7.6 and 6.5. And EBOS wasn't included in the proposal, but there's also, I think, excellent cross-correlation potential there. And of course, between now and the science flight, if there are other surveys like DAISY that would be compelling, we could modify the scan strategy to survey those if there's a better reason to change surveys. So the bottom right shows the CO lines relative to a number of models in literature. So through a range of assumptions in predicting CO, you can see there's quite a range of outcomes. This shows the central value and 2 sigma limits for Exclaim and indicates that we'll be able to differentiate between a range of current models. This has some overlap with the, thematically with the aspects survey. So one way we'll be able to improve on results there is that they have a small region with something like a factor of 3 from cosmic variance, a factor of 3 uncertainty. And this will also measure the integral of CO emission.
On that line, it looks like the airways models differ by like a factor of at least 100, maybe 1,000 in their expected. Yeah, this is the 2011 with the...
Including that, yeah.
What leads to this uncertainty? Like, what do these models assume differently that leads you to this large? That's
something I would like to discuss more offline. I haven't got to the bottom of why, especially VisBall, is so low. Yeah.
And then the green square was tuned for higher redshifts than this. That was originally set up for like redshift 7. It was 2011 model. But I don't know about the VisBall.
Yeah. So in the galactic region, there's the neutral carbon line at 492 that's of interest. We'll also see the 460, the 4 gigahertz 4.3 CO line. So we'll measure both CO and neutral carbon in the galactic region. Okay, moving into the survey strategy, the goal, as I said, is really to primarily through cross-correlation with BOSS. If there's any autopower signal, we'll consider ourselves lucky. The strategy is to cover a large area. So there's a familiar result from the Knox formula for the autopower that suggests that you'd like something like a signal-to-noise of 1 per Fourier mode. And that often drives, in this case, rather small survey sizes. Now for the cross-power, there's more of a second-order dependence on the survey area. And we choose to have currently as large of an area as we can that overlaps with BOSS North to be able to cover as many linear modes as possible, which are easier to interpret. We'll use a cryogenic telescope for faster integration. I'll say more about how that works in subsequent slides, and that's coupled to an MKID spectrometer. This will be from a conventional flight, which means from either Texas or New Mexico, not Antarctica. And that provides an excellent match to Sloan, which is in New Mexico. The goal is to have one engineering flight within 2 or 3 years, and then a science flight following that with 6 spectrometers. So I'll talk about this in terms of a specific instrument and spectrometer, but you can really think, really think of this as, just to wake people up, as a versatile platform for testing far-air technology in a more nearly space-like environment. So this is the instrument concept. It's a large dewar, and the telescope lives inside of the dewar. On the ground, the dewar is filled to around 3,000 or 4,000 liters of liquid helium, so submerging the receiver initially. When it ascends to float, the helium is pumped to 1.7 Kelvin and also a superfluid, so we can use the superfluid fountain effect to cool the optics that are near the exit port. There's enough gas evolution from the top of the instrument to keep the optics clean at float altitude. And this has been something that, well, it sounds crazy, has been flown in Arcade and then tested recently in a Piper engineering flight in 2017. They'll show some results from. So a key part of the story is how we achieve low photon backgrounds. And we would like those because the detectors should have a low enough sensitivity that the overall instrument sensitivity is limited by the photon noise. So we can look at the total power of incident radiation in terms of picowatts per gigahertz. And you can see here for some of the best ground sites, this is for the Atacama, there's quite a high level of incident power. Going to Sophia in an aircraft, there's lower optical depth, and you're starting to resolve some atmospheric lines. And then finally, going to a high-altitude balloon at 35 kilometers, you can see that the background has dropped dramatically. And the integration time goes approximately this squared. So in going from the ground to balloon in these frequencies especially, there's a dramatic increase in sensitivity. Also shown here is a warm window or a warm reflector, and you can see that these emit a background which is still rather large compared to the atmospheric loading. So this suggests that there's a benefit to having a cryogenic instrument without a warm window or reflector. So the other thing you see happening here is that the atmospheric emission goes from being really rather smooth to having some bright lines to having a significant number of lines. So not only is the optical depth dropping as you go higher in altitude, but also the pressure, and so the pressure broadening of these lines. So the lines are resolving into much more narrow features. And that's what allows the balloon float to have such low backgrounds in some of the regions between lines. So that pressure broadening is something like 10 megahertz per torr. And if the bright lines are separated by, say, 5 gigahertz, and you like to be 50 characteristic broadening lengths away from the bright lines, that suggests that you need a pressure of less than 10 torr, which is actually perfect for a balloon environment. So there's an interesting coincidence there. Then to be able to resolve these dark windows, the instrument needs sufficient spectral resolution. So if you have a very broad band, it will catch the bright lines and not be able to take advantage of these dark windows. And that turns out to be around a resolving power of 100. With Exclaim, we like to be a margin of 5 above that. So this is the power in femtowatts for each of the 300 MKIDs in the focal plane that I'll talk about in a later slide. Comparing a warm telescope to cryogenic for this particular case. Converting that to an NEP, this is warm and cryogenic. You can see that the NEP is something like 4 times 10 to the minus 19 watts per root hertz. And that happens to be right at the level of cutting-edge MKID detectors. So this sort of platform is I think, an ideal way to test this technical approach. In the upper bands here, I show the frequencies for cross-correlation with the various BOSS surveys. Okay, because there's a strong ballooning group at Toronto, I thought it would be interesting to look at to describe the atmospheric loading across a wide range of frequencies. So at 100 gigahertz or so, the sky is dominated by the CMB photon background, and that exceeds the background from a warm window. And this is what allows SPIDER to make essentially background-limited observations of the CMB at these frequencies. By the time you get to 500 gigahertz, the CMB is a factor of 100 darker. So that makes the calculation for the photon loading really all about the atmosphere and the instrument. One rule of thumb you'll often hear is that the atmospheric loading at float is approximately equal to a bounce off of a warm mirror or a pass through a warm window. So here I show emission for a reflective for aluminum reflector and one that simulates the SPIDER window. And you can see that if you average this atmospheric emission in a broad band, you indeed find that that's an excellent rule of thumb, that the broadband atmosphere is about like a bounce off of a warm optic. But if you have additional spectral resolution, you can access dark channels that provide potentially much higher mapping speed. So in the case of these, say if this channel is 100 lower, or is a factor of 10 lower than a warm telescope, a factor of 10 in NEP is 100 in mapping speed. So an 8-hour set of data in this channel is equivalent to something like 33 days or an LEB flight in a warm telescope. So there's sort of a trade between having a longer flight with a warm telescope or a cryogenic mission on a shorter flight.
So is that the goal, 8-hour thing?
So the flights are something like 24 hours, but we think it'll be best to observe after sunset and before sunrise, so something like 12 hours is the target. Okay, so now that we have the photon noise, we can convert that into expected sensitivity to the power spectrum. One key ingredient there is the matter power spectrum. That's well known. Another is that there are multiple tracers. So because we're looking in cross-correlation with BOSS, we have to account for the fact that there will be some correlated shot noise with BOSS, and that's described by Volz 2017. Additionally, this is a multi-tracer approach to the large-scale structure. So in principle, can evade cosmic variance. In practice, for this sort of initial detection, it turns out that multi-tracer approach just doesn't make any difference as far as I can tell. So that's really once you're able to be in a sort of mapping regime of very high signal to noise. On the instrument side, you need to be able to accommodate the angular and spectral resolution, the fact that the spectral response is diffractive, so it's a sinc squared, not a top hat. that the noise is inhomogeneous in frequency from the atmosphere. It turns out a good way to accommodate that is through something like the way people treat masks in CMB analysis as sort of an F-sky, a fractional number of modes lost along the line of sight. Additionally, the detectors Fourier sample the spectral response, so several detectors see overlapping ranges of frequency. And then finally, the MKIDs have an interesting set of noise terms on top of just the photon noise that are loading dependent from quasi-particle shot noise. And they also need to differentiate between photon shot noise and bunching noise. So putting those together into some preliminary estimates, this is a forecast for 5.4 CO across Sloan, Maine. And you can see there's some sensitivity to the linear range of the power spectrum, but mainly one halo and some correlated shot noise. Whereas when you get to the quasars, the clustering sensitivity is largely in the linear regime, which I think should be easier to interpret, and a piece of correlated shot noise. The outlook for analyzing the actual data is to look at the likelihood on CL ZZ prime. So to take the set of all cross correlations between each of the redshift slices. This approach has been used in BOSS. So for example, if you look at the XZ core paper, it has a number of advantages, especially for intensity mapping, which I think are interesting. One is that it sort of automatically treats inhomogeneous line of sight noise and weighting, and that's a key element for Exclaim. Another is that it's independent of cosmology. You can find the CLs on a region of sky without gridding onto a co-moving volume. There's also a lot of heritage for measuring CLs from the CMB, both on curved and flat sky regions. You can easily forward model to include instrumental effects. And one thing that I think is especially interesting with this approach is that it automatically does some degree of foreground cleaning. So Milky Way foregrounds will correlate adjacent frequencies, and those correlations show up in the covariance of the set of cross powers. So by having the inverse covariance and the likelihood, you sort of automatically de-weight by those correlated modes. Something I think will be interesting for a number of other, especially a large survey area, intensity mapping experiments. One challenge is that it's not as easily summarized as the three-dimensional power spectrum. If anybody has recommendations there, I'd be very keen to talk about that more. Chris Anderson will be putting out a paper soon to say more about this approach. Okay, moving into the technical side of the Exclaim mission, we'll use an on-chip MKID spectrometer. And this couples the light immediately from free space onto an antenna onto microstrip lines, and processes that light using circuit elements rather than traditional optics. So traditional grating spectrometer will want to add a linear phase delay along a set of emitters or grating. So what we do here is add a phase delay by putting a meandering microstrip in a binary tree into a set of emitters. So, this one will be the most delay, and that one will be the least. And this leads to a set of interference on the focal plane where red light will constructively interfere onto this detector, and blue light will show up over here. So this whole structure is produced lithographically. And that means it's lithographically controlled. So all the dimensions and the fact that you can make 100 little antenna structures here rather than mill a bunch of feed horns. So it's a simpler from the point of view of fabrication, well, in some sense. Additionally, by having the light propagate on these circuit elements, you can see that the phase delay section of the circuit is quite small, and this whole structure is only sort of around this size. On the receiving side, there are planar lithographic antennas that couple the light onto aluminum niobium M-kids, and these are coupled to a microwave feed-out line. And at that point, it's a more standard approach. There's a lot of detail on this slide. I'd be happy to come back to it at the end if people have questions. The optics are familiar from CMB instrument design. So here you have a focal plane, set of baffles, a silicon lens, a window, and these are in a receiver, which couples to a reflective telescope. This is a preliminary, far from final design, but it shows, I think, some of the basic elements. In the science focal plane, there'll be 6 of these on-chip receivers. And many of the technical approaches here, like a superfluid tight window, and we call this a submarine, those have already been tested and have excellent heritage. The focal plane will be cooled to 100 millikelvin using a continuous adiabatic demagnetization refrigerator. So this is a test device that we have in the lab. The way these work is that a crystal in the bore of a superconducting magnet provides cooling. And ordinarily in a refrigerator, you think of, say, a piston interacting with kinetic degrees of freedom in the gas. In this case, the magnet is interacting with the spin degrees of freedom in the crystal. And each one can cycle heat out of progressively lower temperatures to the 100 millikelvin stage. It sounds somewhat crazy, but these are actual lab test data of the continuous ADR, showing here that the coldest stage just remains at 100 millikelvin, and it does so with something like 10 microwatts of cooling power. The Cryogenic Telescope also has heritage from the Piper mission, so here I show a cross-section of that. This is really quite a bit more complex as an instrument, and in its study, the goal here is to measure the CMB B modes, and this uses a polarization modulator coupled to a reflective telescope and a receiver. This is a whole other talk unto itself. But we use a number of elements from that that are essentially built to print. So there's a set of flight electronics. This is the Piper gondola on the flight line from an engineering flight. And this is in the process of a helium fill. So you can see that well, I'm about this tall, so it's really quite a large doer. Let's see. So there was an engineering flight in 2017. It's not every day that you get to loft 4,000 liters of liquid helium into the upper atmosphere. So it's fun. I think it's fun to talk about this this plot of the temperature during the flight. So the receiver starts here, and it's sitting initially partly submerged in helium. So it's at 6 Kelvin. The optics are up near the top of the instrument and sitting around 90 Kelvin, so quite warm. Now, as the balloon ascends, the helium is pumped by the falling pressure of the atmosphere. So there's rapid gas evolution, and that sort of flash cools the optics. And then by around 80,000 feet, the helium goes through a superfluid transition, and the boiling settles down. And at that point, you have a superfluid and a weak vacuum above it, and the optics can then start to warm up. It turns out they only warm up to 30 Kelvin or so warm relatively speaking, but still actually a cryogenic telescope. We then use superfluid fountain effect pumps to cool the optics, and you can see that we turn those on here, and the optics and receiver then are sort of rock solid at 1.7 Kelvin. In the engineering flight, we turn that off briefly, and you can see the temperature jumps up as the the optics can warm in the upper part of the instrument. This increase at the end is from a sag in the balloon altitude, but generally it's in the main part of the float. It's quite stable in temperature. We're in an incredibly fortunate position now that there are not one but leave it on the floor. There are not one but two intensity mapping balloon missions being funded by NASA. So I've talked about Exclaim. The other one that was recently awarded funding is TIM, which was previously known as Starfire. So I'll talk about some of the differences in the strategy. I think in this early phase, it's good to have some orthogonality in approach. So the approach here is to use a 2-meter telescope with heritage from BLAST at ambient temperature. The focus here will be on higher frequencies. So this uses a direct coupling to the MKIDs rather than antenna coupled. The primary science will be on a smaller region, around 1 square degree. And with the warm telescope, there's a great benefit from having a longer duration flights. This will be an Antarctic campaign. Primary science will be C2 in autocorrelation, C2 cross N2, and both of these with stacking of overlapping surveys. This is also an MKID spectrometer, but it's a free space grating. Yeah. So this is a summary of the Exclaim parameters. There are a lot of details here. I'd be happy to put this up at the end and talk about those. I'd like to move back out to a discussion of challenges in intensity mapping and some directions forward. It's often thought that intensity mapping is a new approach, but from the work of Hogan and Rees, you can see that it actually dates back quite far, almost as far as the CMB. So you might ask why it hasn't flourished in some of the same ways as the CMB. And there are programmatic and scientific interests that have shifted, but a real, one of the reasons is that the sky can be quite bright in the frequencies of interest compared to the expected lines. So it doesn't leap out of the map like the CMB does for Planck. One challenge due to foregrounds is in a basic issue of subjectivity in cleaning. That is, we don't know the covariance of the Milky Way foreground well enough in advance to be able to write down the modes to remove or the covariance that best weights the data. So there's always some knob to turn in the cleaning, which is really how aggressively it's cleaned. That is how much deweighting there is. So if we look at the cross power, as you deweight more and more foreground, if you correct for any signal loss, that cross power should remain constant. But as you remove foreground, the errors will fall in the cross power as the variance drops. But then at some point you can have the risk of removing more signal, in which case the errors will grow. And in the space of deweighting, there's a clear optimum cross power. So you can optimize the parameters of the cleaning to achieve that. So now if we look at the auto power, say at some band power, as you deweight more of the foregrounds, there will still be some, you can think of them as residuals that continue to fall as there's more and more deweighting. Now again, the errors will drop as you get rid of variance, and then they will increase as you get rid of signal. So one thing that does exist in the auto power is a least upper bound. So in this parameter space of weighting, there's some best upper bound. And that may be at a different point than the best cross power, but it does exist. But at what point here would this be considered a detection of the autopower? Okay, so one approach here could be to say that you reach a plateau, and that at this point this is a detection of the autopower. But a possible concern is that this would be a plateau of contaminated modes, so that by cleaning further, you start to remove some of those modes, but also perhaps much of the signal. So there's, I think, a basic challenge of additive bias in the autopower. So as much as possible, if experiments can accommodate that additive bias, for example, by detecting a BAO feature on top of an additive bias, those are good strategies, but always admitting that there could be some unexplained variance. So cross-correlation has become a gold standard now for unambiguous detection of line intensity. And this avoids interlopers, so lines at other redshifts. It avoids the Milky Way, which is uncorrelated, and any instrumental response, which isn't accounted for. It also allows you to avoid cosmic variance in much deeper surveys. And there are a number of interesting approaches that you can do that combine the auto and cross power, or the cross power with different subsamples. So it's a very powerful technique for astrophysics. So there is one significant challenge with the cross power, and that is from correlated continuum emission. So it's often assumed in intensity mapping that galaxies emit a single line, but in fact they have a complete SED. So there's synchrotron and dust emission in the radio, and then moving into the far IR and near IR, there's quite a bit of complex structure. So this complete SED also has to be accommodated in the cross power. So the way that shows up is the following: that in the usual picture you have one redshift mapping to one frequency in the data volume. But if there's a continuum in the SED of the galaxies, then these redshifts will also show up at some other frequency. That means that this frequency will cross-correlate with this redshift. This was first pointed out in a work by Paulo Serra, 2014, looking at the cross-correlation of Boss LRGs with Planck. And the paper doesn't mention it, but I think one of the goals was probably to detect C2 emission, and they found this correlated continuum along the way. So in each of the Planck bands and Iris, there's a strong cross-correlation signal with the Boss LRGs. So you can think of this, what this is doing is really measuring the SED of the galaxies at the redshift of the LRG sample. So if we look in a little bit more detail for C2 in the Planck data, this is the Boss North region. And here you can see the total autopower, and that's dominated by the Milky Way. About a factor of 10 below that is the correlated continuum, and another factor of 10 below that is C2. So this gives a sense of the sort of scope of the challenge. So in this particular case for Planck, because the frequency band is so wide, the cosmological density contrast is washed out, and so the C2 is lower than it would be for a true tomographic measurement. But you can see the scope. So following Serra 2014, Anthony Pullen has led a nice series of papers looking for C2 emission in Planck. And again, every band, 353, 545, 857, these all cross-correlate with Sloan quasars and CMAS. So the approach he takes is to marginalize over a model of the CIB, or the SED of the galaxies. So that has some brightness of the dust SED, evolution and temperature. There's also SZ that has to be marginalized over, and all of that has to allow C2 to still be detected. So we put out a paper recently improving on a 2018 release by making a more accurate covariance model. And that has allowed now a strong detection of an excess that's consistent with C2 emission. But this really, I think, is stretching Planck and Boss data to their limits, and we need new experiments to make this more definitive. So it's convenient to think about these continuum emission terms in terms of a number of degrees of freedom. So an instrument will need enough channels to be able to suppress the uncorrelated continuum, the Milky Way, to suppress the degrees of freedom in the correlated continuum, and then still have signal directions left to determine the line amplitude. So in practice, this would require something like 10 bands. So with Planck's 3 bands, this is an incredibly difficult measurement. So here's an example that I've cooked up where there are 3 modes of continuum contamination, just as an example, where if you only have 3 bands, the error is boosted quite a bit by this variance where there's just no degree of freedom there's no leverage to pull it out. But by simply adding 1 more band in this toy model, there's a significant gain in sensitivity. So that's kind of the regime that this Planck measurement is in. The good news is that essentially all planned and current intensity mapping experiments will have hundreds of bands. So there are numerous degrees of freedom for handling these other contaminants. So we can think about that now in terms of the 2D power spectrum, so the power spectrum along the line of sight and the perpendicular direction. So the SED is a convolution in real space, and that makes it a multiplication in K space. So you're multiplying the underlying power spectrum by the Fourier transform of the SED. And because the SED is spectrally smooth, that correlated signal shows up at low K parallel. So by cutting low K parallel and barring other instrumental effects, you can very effectively throw out these contaminated modes. So this shows the total number of modes as a function of K, both before and after this cut. So you can see there is loss of signal on the largest scales, but it's fairly robust going to higher K. I'd like to close by taking a step back and considering intensity mapping as a method. And this is sometimes cited as a fault of intensity mapping, that it's just a method. It's not specific science in a way that, say, the CMB might be. So I think it's important to look back at the history of and value of methods and technical approaches. So going from the invention of the telescope, for something like 150 years, telescopes became larger and larger, but in some sense, as a gross mischaracterization or gross simplification, there was a stagnation. One of the games people played with larger telescopes was to resolve more and more double stars. It was really with the reintroduction of dispersive spectroscopy that there's much more contact with physics and a much broader set of outcomes. And again, spectroscopy stimulated studies of the black body, which arguably stimulated quantum mechanics and the CMB. So we're now in a regime where CMB instruments are becoming very large and optical instruments are becoming very large. So one of the hopes of the intensity mapping community is that by sort of combining this in a new technical approach, that we can still do compelling science with more modest instruments. And a final point is that with any new technology or new way of looking at the sky, there could be unintended discoveries. I think the FRBs in CHIME are a great example of this. So to wrap up, intensity mapping has numerous applications and significant experimental effort behind it now. The particular mission we're pursuing at NASA at Goddard will map CO and C2 from redshift 0 to 3.5 using a new type of on-chip spectrometer coupled to a cryogenic telescope. This is really primarily in cross-correlation with BOSS. Intensity mapping does have interpretive challenges, but I think that the tomographic cross-correlation remains as a robust measure. Thanks. I'm happy to take any questions. Really?
So over the various frequency bands that Exclaim measures obviously show that predictions are all over the place. However, are the uncertainties in predictions over those frequency bands or over those redshifts rather uncorrelated uncertainties? Like, is it likely that that one of them is likely right, or are they most likely correlated, that either you see them all or you see none?
I think it's quite correlated. So, so by measuring across multiple redshifts, they do sort of trade places. So it's not the same model, which is always the brightest or the dimmest. Well, I guess the dimmest is probably almost always the Visbal 2011. But there's significant. By having multiple redshifts, you can hopefully see the same evidence for the same model.
Could you imagine cross-correlating with other CO or C2 experiments, like ones from the ground, or is the survey strategy just C2?
Absolutely, yeah. So one challenge with cross-correlating pure intensity is that there's correlated foreground. But one thing that I think could be quite interesting is looking in regions where there's a cross-correlation. So there's a galaxy survey, C2, and a CO survey. So you can measure both the neutral gas and the C2 in the same regions. So yeah, for example, for COMAP, I think we'd be very interested to see if we can overlap. The survey area for this is rather large. But yeah, so there's some sort of, that's the main compatibility issue that I would see is the survey size. Chris?
Can you say a little bit more about the confusion associated with a given band probing different lines at different redshifts? And how that source of confusion is more or less important depending on which type of line you're looking at?
So with cross-correlation with BOSS, we can look for a structure that's coherent in the large-scale structure and the line. So that allows one line to be isolated from interlopers. Did I gather?
That's a correlation. That's not a pure one-to-one. I guess you're statistically expecting one particular line to have a stronger correlation.
Yeah. So the interlopers do add additional variance, even if it doesn't correlate. Maybe we can talk afterward.
Well, I think that's probably as good a time as any to say, let's thank Eric again.